Welcome, everyone. Good evening, good morning, depending where you are. It's my pleasure now to talk about new digital production technologies for printed electronics. I would like to give a short introduction, then speak about digital production, explaining a little bit technologies and processes, and how we can bridge the gap between the traditional technologies we're using today in printed electronics and digital production. Short introduction, Coatema coating machinery is existing since 1974. We are focused on coating, printing, and laminating technologies. We are global market leader in a lot of high-tech areas, from print electronics, renewables, pre-preg, and pharmaceutics, for example. Company vision is from lab to fab, means from the small sample to the final product. We are scaling up our customers. We have Europe's biggest R&D center, with over 14 pilot lines in operation, doing a lot of services for our customers. And we are, since 2018, part of the 88 holding. The 88 holding in Hamburg contains of Krönert, Dreitec, and ZAE drive systems, and us. And this means 450 people. And it's one of the biggest holdings in Europe on coating, printing, and laminating technologies. What means digital production? When we started print electronics, and I remember our start of Coatema in 2002, we said, okay, we're using printing, coating, deposition processes, we're combining them with chemistry, and we're replacing silicon wafer technologies in microelectronics. And the advantages are our products are flexible, thin, robust, and lightweight. This was our story for a number of years. What we see today, of course, is that we have more and more integrated devices. So we're using silicon technologies and printed electronic technologies, like you can see here with this smart shirt out of wearables. And if you see on the left side, we started there in 2008 in European projects where we combined printed solar with printed batteries, printed bus bars, and a chip to control the power supply into the battery. So the idea always was printed electronics can be used on these type of devices. So the question is, how do we get there? In the beginning, of course, and still today, we started using traditional printing methods like screen printing, flexo printing, gravure printing, and you see here a few systems from Coatema coating machinery, which are in operation for quite a while in print electronics. But of course, we're now moving into digital fabrication. What is the biggest advantage of digital fabrication? It's that the lot size one is real. So you can do one product for the same cost like millions. This is true at the moment for additive manufacturing, 3D printing as one point. But at Coatema, we have the target to develop digital fabrication systems where we also can do our products in lot size one. Why? We think that printed electronics has a big future, specifically in Europe, if you see wearables, sensors, integrated smart systems, and specifically Internet of Things. If you use technologies which differentiate us from mass markets or mass production methods in Asia. This means localization of production. So in the area where you're selling the products, you're producing them. It means using Industry 4.0. It means using digital fabrication and additive manufacturing in combination. And it also means to use big data in your process to produce print electronics. And we at Coatema, we use the word Manufaktur 2.0 with digital fabrication, because that's the way how Europe started 100 years ago. Small factories in houses producing goods which are being used directly at the site where they were produced. So you can do one size for the same cost like millions. You have manufacturing at site. with personalized design for each customer. So a big USP in this approach. It will change global manufacturing to local manufacturing, sustainability, circular economy, reducing your carbon footprint. It will be a productivity boost for the old economies and Europe, and it's the real fourth revolution. So the manufacture, like it was 100 years ago, also in Germany, will come back as the digital manufacture 2.0. That's the idea of the talk. So we are looking into sustainability, we're looking into personalized products which are produced at place of use, which have a low carbon footprint, no more shipping, which are digital, and which are produced on demand. So from globalization, specifically in these difficult times, to localization of production, that's the idea of the Digitale Manufaktur 2.0. And this, of course, in combination with the ideas in printed electronics, where we're combining different products in one wearable device, like you can see here, with energy harvesting, with different technologies, sensors, actuators, but also maybe an NFC tech or 5G to supply the communication. And of course, we can use a lot of different processes like printing, coating, inkjet, laser, additive manufacturing, nano imprint to produce these different type of products. And we also should look into energy harvesting or making these products independent from power supply, so using solar, fuel cells, and batteries. Important for this, and this we learned over the last 20 years in print electronics, we need to develop design principles, standardization in the industry, also for digital fabricated products. That's quite important to keep in mind for the rest of the talk. What are the technologies and processes to make this happen, to make this possible? First of all, we are facing the same parameters in digital fabrication we also face in our normal coating or printing operations. So from coating chemistry to controlling the environment, drying processes, process control, the process analysis, process parameters are as many. We look into surface treatment, we have printing, coating, digital fabrication methods like inkjet printing or laser patterning. We have lamination, encapsulation, and pick and place. The idea here is always from lab to fab, so from the small lab scale tabletop system to pilot to production, to have reproducible processes which are economical and give a market advantage. Point is, of course, one printed electronic product are several layers, up to 10 different layers, different functionalities. So we have to combine these processes in a smart way to be able to produce either on big scale or on small scale the different type of products. You see here an installation we did in 2011 in Finland at Printercent. At this time we were looking into big scale upscaling of printed electronic processes. And if you look into these processes, we looked into process parameters like operation speed, precision of coating operations, tension control. And what we also looked quite early was artificial intelligence for the analysis of all these parameters and machine learning. Because if you want to go into high accurate processes, you have to improve today's operation. So besides looking into topics like tension control, registration control, we have to add in process analysis, again, artificial intelligence to make our processes more reproducible and more independent from the operator. We have to invest a lot, and this we're doing, into quality control, which also means to see the function of the device or layer in the process in your machine. And we were producing a lot of data, so we have to use big data, cloud solutions, combined with AI to see what's happening in our processes. And on all these topics, the complete ATH group is working. And we started there quite early, in 27 in Greece. at the University of Thessaloniki. And here we already looked into measuring and controlling of our standard, and at this time also digital processes using laser and inkjet. I'm not going to detail here, but you see all the different points where we measured, where we controlled. 20 meters of operation. I'm not going to detail here, but you see here the different processes like printing, slot die coating, laser scribing, registration control, which was very accurate, again printing, and here we had the first inkjet system in, where we started first processes in digital fabrication. Till winding on the material, and of course at this time already very unique inline quality control with ellipsometry and inline Raman. And this unit at the moment will be upgraded in the European project Real Nano to have more inline quality control functionality. So 90 meter in length, 30 meter per minute production speed, but still a working width of 300 millimeters, so not a big scale operation. Here we use these systems, but of course we looked into inkjet. Inkjet means drop on demand. There are a lot of different inkjet technologies, but we looked into drop on demand the next 10 years then. And we looked into the deposition of functional fluids. So we're not interested in graphic arts with inkjet. We're not interested in latex and other applications. We are looking into deposition of functional fluids, which either can be aqueous or solvent-based. The way how we want to do it, and that's a project which is running at the moment in our company. We are the equipment provider. We will have ink suppliers, and we already have one ink supplier, Jens Ink, which is our cooperation partner. We will have developers for the engineering process for our customers, and we will have print module integrators, which integrate the print module into our machine. And after this step, we are starting to be a system integrator, delivering the complete service for our customers in print electronics, in medical applications, but also in battery and fuel cells. So it's a little bit different approach here in the digital fabrication than we do normally. We don't try to invent everything ourselves. We are working in networks, in corporations globally to have the best result for operation. That's the old system in Greece, Inkjet. In between, we started our own development. Here you see a Fujifilm Dynamic printhead in operation on our machine. We learned a lot here, also on fluid recirculation systems, on the overall control of digital printing, which also includes drop watching systems, in integrating NIR and photonic sintering, for example, and of course also artificial intelligence to detect if a nozzle of a printhead is closing. Idea at Coatema is always to scale up. So we will install a 300 millimeter system either this year or beginning of next year in our R&D center for a complete inline process on 300 millimeters. And then we want to scale up to 500 and 1000 millimeters. Designs are ready. You see on the front part of the unit, the inkjet system, which of course has also to fit into the existing frame of our units, so that it can be combined, for example, with NIR, with normal electric heated dryers. We can integrate different inkjet systems into our units. We have done this already at some exhibitions, where we demonstrated also these print capabilities. And that's the first part beside the laser patterning of digital fabrication in our operation. Another system we're using on a daily basis, which is totally not digital, we also want to bring into the digital world. So slot die coating means coating a full area of fluid out of a closed chamber with the pressure control forming a meniscus. And with this, we get very precise, very thin layers under 1 micron onto surfaces. These are high-quality tools where you can have very accurate coatings from left to right. But of course, and this we started in flexible solar cells around 2005. Here we wanted to have stripes, not full-scale coatings. So we developed the so-called meniscus guide. And of course, people looking into intermittent coatings in this area, and maybe, and I'm saying here really maybe, arbitrary patterns in the future, which would make the system completely digital. This we did here, very basic, intermittent coatings for battery applications, a hot topic today, of course, but a proven technology. Not too fancy, not very digital. So what we thought about, okay, what are the technologies for this intermittent coating processes? And we developed in a European funded project, PyScale, a slot die coating system, which is intermittent and which can work with low viscous media for OLEDs, for example, and where we're closing and opening the slot die lip mechanically with the piezo. So that's the digital part. We can run a specific ramp with the piezo, with this mechanical movement of the slot die lip by 300 microns, so not a lot. And you see here the ramp we can operate. So here we're going into digital operation of our slot die systems, of our pumps. And you see here, at the moment we are still at stripes coatings, but it's a big step forward in our standard operations, also bringing them into digital operation. I would like to finish in time, as I see, with our ideas of bridging the gap. Of course, you have to have reproducible results in every step of scale. This is very important, specifically for technologies like inkjet printing. And we at Coatema and myself, we are looking since 15 years in inkjet printing processes. We now think inkjet is stable enough to be scaled into production processes. You have to do a reality check if the approach is really scalable. Think about of spin coating not being scalable and being replaced normally by slot die coating. And of course, your approach has to work in real-life production environment. It can be rocket science, but then it still has to work. Everyone has to reach economies of scale as soon as possible. There's a global competition on this. And sometimes the question for printed electronic products, do we really need 5 years of lifetime, or is 1 year of lifetime totally enough? Standardization, I mentioned before, and maybe small, which means Manufacture 2.0 is the new big thing for Europe. So think about the container with Coatema equipment in your backyard, producing the lot size 1, totally custom made for a specific customer project, and then being moved into the next location, producing a different product. That's the vision, of course, we have at Coatema. And to stay in time, I now have time to answer questions. Thank you very much for your attention.
Thank you, Thomas. So far, we don't have any questions in the chat, although I find your Manufacture 2.0 very fascinating. Can you maybe talk about some applications for this?
Yeah, one application, for example, we have a lot of pharmaceutical applications where people combine printed electronic with pharmaceuticals, so that, for example, a patient gets exactly the dose of medication he needs over the day, like in transdermal systems. You get more and more personal medication, which is being produced in small quantities. So if you stay in transdermal systems, it could be a specific transdermal system which is made for one patient and is covering maybe 3 months, 4 months of the amount he needs. And this you can do for 20, 30 different patients. And the same unit then also can be switched to producing sensors for a specific operation. I think the advantage is here, you directly produce at the site where you're using the products. And if you see the discussion on sustainability, on circular economy or low carbon footprint, I think this makes a lot of sense instead of shipping products from Asia, for example, to Europe.
Okay, we have a feedback from Brad Miller. He would have liked to have your talk last 40 minutes instead of 20. So that's a nice feedback.
Okay.
We have also an article by Coatema in the latest issue of OPE Journal. It's about electroluminescent textiles. Can you talk about that maybe?
Yeah, we have done several funded projects. We also have a team member, Kira Stefan, which did her bachelor on this topic. So let's say it's a basic way of doing printed electronic products on textiles, but it gives the opportunity to do this on big scale areas. Let's say replacing wallpaper with a textile structure where you can produce light or optical effects. This was of a lot of interest for the traditional textile manufacturers in the processes, in the projects we did.
We have a question by Hossein Rahimi. He wants to know if you also have developed any R2R encapsulation machineries.
Yeah, we do them a lot. We work with encapsulation technologies, let's say with barrier films which have a PSA adhesive on. We can apply UV cross-linking hot melts onto barrier films, and we can do these processes from top and bottom. We can do them under a nitrogen or argon atmosphere, or we normally do them under this type of atmosphere. And in the overall ATH group, we have done these systems also already up to working with of 2 meters.
Okay. Then we have a question by Daria Wieczlawska. Great presentation, Thomas. In terms of inkjet printing, which parameters of the inkjet ink or the properties of the final printouts performance would be the most important for your current projects?
Definitely the viscosity range an inkjet can be operated. And specifically the reproducible viscosity range of inkjet inks which are being supplied. So we had sometimes surprises that viscosities changed by different lot sizes. So controlling the viscosity before inkjetting, I think that's one of the most important parts. The other thing, of course, with inkjet, everyone wants to do very fine lines of application. So you have to optimize not only the ink behavior, the jetting behavior, your substrate surface tension, but also the drying or annealing processes afterwards.
Okay, thank you. Then we have a follow-up by Arthur Hensby. He wants to know what are the first applications that you're interested in for the inkjet printing of functional inks?
The first applications we're using inkjet in had been, of course, and that's quite a while ago, organic photovoltaics, replacing screen printing of silver grids. We are now looking into touch panel application, so doing very fine lines, and also some other busbar applications for interconnecting of different print electronic devices.
Okay. I think we don't have any more open questions. It's the final chance for you to ask Thomas. Anyway, once again, thank you for this fascinating lecture. And again, please make sure to also visit the Coatema booth. Thomas is available with a rather large team here at the event.